Capacitors can act like shorts or opens. So before we get started, we should talk about the language of switches. A switch closes at t equal to 0. This implies there are two intervals relative to t equal to 0. One, t equal to 0 minus implies just before the switch is closed, the switch is closed or open, the switch is thrown, and then t equal to 0 plus, that implies just after the switch is closed or opened. So now, let's talk about them acting like a short. So capacitors acting like shorts. At t equal to 0, 0 plus that is, the capacitor at that instant has not built up any charge on its plates. Picture-wise, I imagine that I have this, let's say that we're looking at the top surface. So if we're looking at the top surface, you could imagine that this right here is the metal conductor here. And on this metal conductor, of course, is a wire attached. And so what we're looking at is that we're looking at the charges that are just right there above it. So as soon as the switch is thrown, there is some movement, but none of them have actually gone onto the plate. So once again, these guys are what? These are the incoming charges. And you're seeing here that there is no charge, no extra charge on the plate. Again, at this brief moment, there is no voltage across the capacitor. From the capacitance, the capacitance equation, we see that VC is then going to be Q divided by the capacitance, but if there's no charge on the plate, Q is 0, so therefore its voltage must be 0. Anytime an element has its voltage being 0, it acts like a short. And this is primarily the reason because this comes from Ohm's law. Therefore, an uncharged capacitor acts like a wire or short circuit at t equal to 0 plus. Now, the capacitor can be replaced by its equivalent. And in this case, its equivalent is that if I have an uncharged capacitor, that is, nothing is on that plate. In this situation, we then say that C at 0 plus is 0. So now I can replace in the circuit for that brief moment, I can replace this with a short, where now VC of 0 plus of that short is, of course, 0. Capacitors acting like open circuits. So why is there current flow when a capacitor is in the circuit? There must be a potential difference between the power supply and the capacitor. There must be a potential difference between the power supply and capacitor. When there is no potential difference between the two, then there is no electrical pressure acting on the charges and no current can flow. Picture-wise, how does this look like? So remember, we have to be in potential space. So these images occur in potential space, electric potential space. So let's see if I can draw and modify these guys. So I have an incline. So here's my incline. And if I have a grounded capacitor, then I imagine that when I'm looking at this capacitor, I am saying that this guy is grounded. So I'm going to place my ground right here, and I'm going to say that that's 0 volts. So the moment the switch is thrown, so once again, remember, we are plotting the voltage of the capacitor as a function of time. And then here is our time axis. So at t equal to 0, 0 plus, there's no charge on the capacitor. So then VC here has to be 0. Let's write this down. So at t equal to 0 plus, the capacitor is grounded. Where there is no charge or voltage across it. In other words, it's temporarily at the bottom of the potential incline. So we need to look at the voltages. So now focus on the potential differences between the source and capacitor. At this point, we have to say that the source voltage is this high right here. And so when I look at this guy, we can clearly see that this guy is the source voltage. So where is the capacitor at? Well, the capacitor has a voltage of 0. So now you could see here that from here to there, this gives you a max potential difference between the source and the capacitor. So now what starts happening? So what starts happening here is that if I take the same picture and slightly modify it, what am I seeing? I'm going to put this guy right here. And so now what we're at is that we're going to be at a time of between 0 and infinity. So I have to modify my incline here now, because what I'm seeing is that now the capacitor has climbed. It has climbed up the incline because there's charge flowing now. So I still have my capacitor, but what you're seeing here is that now it is moving up the incline. So then we have to say then, let me move this up here a little bit just to have space to write down. We could then say that as charge starts building up on the plates, the voltage Vc of t increases since we still have voltage of the source greater than the voltage of the capacitor. In other words, the capacitor starts climbing up the potential incline. So here we're seeing that we do have a buildup of charge across these. So now if I start looking at what's happening here, well, height-wise, we still have a potential difference. But now what's happening is that the voltage of the capacitor has now increased. But there's still a difference between the two. And you could see that these heights still have a difference, so therefore current continues to flow. So if I now copy this again, I'm going to place this over here, we then reach our final stage here. And so what happens in this final stage? At some point, if this represents the maximum voltage of the source, then right here, that has to represent the maximum of the source in this final stage here. So now the capacitor has now climbed up all the way to the top. So if I come in here and I draw it, I'm then going to say that, yes, the capacitor now is up here at the top. And when you're looking at the height difference between these two, you can see that they're exactly the same here. So when I now look at the height of the potential here, we can see that Vc and Vc source are now the same, which implies then that the potential difference now is equal to 0. So if I write that up, we then say that when the capacitor has climbed to the very top, the potential difference V source minus V capacitor is identically 0. Therefore, there is no potential difference to drive the current. At this time, IC, and typically we say it's at infinity, is equal to 0, and the capacitor is fully charged. And acts like an open circuit. One can replace its steady state equivalent as I have a capacitor that's now fully charged. In other words, it has all the charge that it could hold on to. At this moment, we then see that the voltage across this capacitor is the same as the source voltage. When this happens, this current IC is equal to 0. The only time I can have that is if the capacitor acts like an open circuit. So once again, we have a capacitor that has a voltage of VC, but its current is 0.